Welcome to homework.
Okay, so we have a calorimetry problem here involving the combustion of benzoic acid in a closed system, in a calorimeter, and in water. So we know a little bit off the bat. We know since it's a combustion that the overall temperature change of the system is going to increase. So we know that delta T, which is what we're solving for, at the end of this should be positive. And we know overall that in equilibrium, the heat gained is equal to the heat lost. So Q is equal to negative Q of the system. Now we can set this up as sort of a system of equations here where we know that the heat that's going to be given off by the combustion of the benzoic acid here is going to be equal to the heat absorbed by the water as well as the calorimeter. Those have to be both included in order to see the transfer of heat and the equilibrium to be reached. So let's first look at the heat given off by the combustion of benzoic acid. So we know the mass of the benzoic acid sample is 1.2 to 1 grams, and we know that the enthalpy of combustion is negative 3,227 kilojoules per mole. So in order to solve for the heat given off, we can use the simple equation where the heat is going to be equal to the enthalpy of combustion multiplied by the molar value of the sample. So first we need to figure out how many moles of benzoic acid we have. So we know N here is going to be equal to the mass of the sample, 1.221 grams, divided by its molar mass. And the molar mass of benzoic acid is 122.12 grams per mole. The grams cancel, and we're left with a molar value of 0.01 moles. So next is just to figure out the heat of combustion of the benzoic acid. And that's just going to be simply multiplying this enthalpy value that was given, which is negative 3,227 kilojoules per mole, by the amount of moles of sample that we have, which we just calculated at 0.01, and we are left with negative 32.27 kilojoules. Now we know since this is a combustion and that it's exothermic, it's going to be giving off this heat into the water. So we know that overall the temperature is going to increase in the system. So in order to input this into the other equations, we're going to take the positive value of this. So this is going to become positive 3,200, or 32.27, sorry. This will just make everything more easy to solve later on. So now let's look at the heat of the right side of the equation of the water and calorimeter. So we know the mass of the water inside the calorimeter is 1.2 kilograms. Now this should be converted to grams just so it's easier to use the specific heats given. So you simply multiply by 1,000 to get your gram value. So it's going to be 1,200 grams. And then both the specific heat and heat capacity of the calorimeter water are either given or known. So in this case, we can just get right in, and we can say that the right side, so the heat of the water plus the heat of the calorimeter is going to be equal to MC delta T for the water, so 1,200 multiplied by the specific heat capacity of water, 4.184, multiplied by the change in temperature, which is what we're solving for, all of this, plus, now we have to do it for the calorimeter, which is just this, the heat capacity given, since we're not taking into account the mass of the calorimeter, multiplied by the change in temperature, and multiplying across and combining everything, we get the right side of the equation is going to be 2 6,385.8 multiplied by the change in temperature. So now we have the left and right side of the equation, so we can go ahead and combine those. Now, one final thing we do have to do before we use this equation is we know that the left side of the equation was done using the specific heats, and they were in the value of joules. And then the right side of the equation, the enthalpy, was in kilojoules. So we just have to convert one side to match the other. So what we're going to do is we're going to convert the right side to joules. So we're just going to multiply by 1,000 just to do the conversion. So this becomes 6,385.8 multiplied by the change in temperature is equal to 32,270 joules. So when we do our division here, we find that the change in temperature is equal to 5.05 degrees Celsius. So to recap, when we are doing a calorimetry problem, we need to make sure we take into account every aspect of the system. So we have the item being combusted, the benzoic acid, the medium it's in water, and we cannot forget about the heat that's going to be also absorbed by the calorimeter.